Every time you open a door, turn on a water faucet, or tighten a bolt with a wrench, you exert a turning force which we call a torque. A torque is a twist or turn that causes a rotational acceleration. In the English system, you're probably more familiar with measuring torque in something called foot-pounds. However, in the metric system, we use instead something called a Newton-meter. The symbol for torque is a scripted letter T, which is actually a Greek letter called tau. Now, the one way that torque is different than force is that torque depends on both force and leverage. The longer the lever arm, the greater the torque that is applied, the easier it is to twist or turn an object. For example, you use leverage when you use a claw hammer to pull a nail out of a piece of wood. So let's say you have a nail in a piece of wood, and so you use the end of the hammer here, and the handle itself gives you some leverage so that when you apply a force, it's a lot easier to pull out the nail if you apply a force really far from the head of the hammer. Now, the longer handle of a crowbar provides even more leverage and makes it even easier still to pull the nail out of the piece of wood. Another example of using leverage in order to get as much torque as possible is when you have to open a jar. If you have to open a jar, maybe you aren't strong enough to open it just by using your hands. So instead, we use something called a strap wrench, which extends the lever arm when opening the jar. Some different designs of using torque to make it easier to use would be like a doorknob. The doorknob on the left is what we typically see. It has a very short amount of leverage, not much leverage here. And so for those that may have arthritis or those that are physically handicapped, it is very difficult to open a door with just a knob for a handle. So instead, to make it better for those with arthritis or for the physically handicapped, we use a doorknob like this on the right, where we can get more leverage by applying the force further from the actual point of rotation. So the farther we are from the point of rotation, the more leverage we have and the easier it is to rotate. In other words, we get more torque for the same amount of force. Another design which uses the idea of torque is for a faucet handle. So you might see a faucet handle in the classroom, something like the one on the left. But again, for those that have arthritis or those that are physically handicapped, it's very difficult to turn a knob like that, to produce enough force to get the required torque to turn that faucet handle. So instead, we have faucet handles for the handicapped like the one on the right. It provides a longer leverage, and therefore it's easier to turn for the same amount of force. Another would be like a water shutoff valve. So a typical water shutoff valve would be something like the red one on the left. But what happens is over time, you may get some calcium deposits that build up in the pipes and also where the mechanism is to turn. And so it's very difficult to turn that knob. So instead, what they do is they have one that has a longer lever arm. And therefore, you can turn it a lot easier, get more torque for the same amount of force in case there's any kind of calcium deposits that have built up over time in the turning mechanism. So the longer the lever arm, the greater the torque. One example of this as well is a doorknob. A doorknob is placed far away from the hinges, which increases the leverage. So it's easier to open a door if we place a doorknob way over here as far from the hinge as possible. If you were to place the doorknob over here per se, it would be a lot more difficult to open the door. In opening the door also, you push perpendicular to the door. You push at a 90-degree angle. By pushing at a 90-degree angle or perpendicular to the door, this gives more rotation for less effort. When the force is perpendicular, the distance from the hinge to the point of contact is called the lever arm. Sometimes it's referred to as the radius as well. And so here is our formula for torque. This scripted T, which is actually a Greek letter tau, represents the torque measured in Newton meters. F represents the force measured in newtons, and R represents the radius, also known as the lever arm, which is measured in meters. With this idea of leverage, we see that we can get the same torque by either applying a large force with a short lever arm, or by applying a small force with a long lever arm. So it's always a trade-off. In order to get the same amount of torque, you could either apply a large amount of force and a small radius, or you could apply a small force and a large radius. Now these three examples down below, although the magnitude of the force applied are the same in each case, the torques are going to be different. In the first situation, since we do not apply the force perpendicular, that is going to be less torque than if we apply the force at a 90-degree angle to the wrench. If we want to get even more torque than the second situation, what we can do is we can place a bar over the wrench itself to extend that lever arm or radius. And so for the same amount of force, we can get a lot more torque produced. So here's a situation. Let's say you cannot exert enough torque to turn a stubborn bolt, as shown down below. Would more torque be produced if you fasten a length of rope to the wrench handle as shown? So take a minute, think about your answer, write something down in your notes, and when you're ready, unpause the video to see what the actual answer is. Welcome back. So we were seeing if this would produce more torque if we simply apply or tie a rope to the wrench. And the answer is no. Because the lever arm is still the same, we do not increase the amount of torque. The lever arm is the distance from the points of rotation, in this case the bolts, to where the force is applied. In this case, it's still at the same spot. To increase the lever arm, a better idea would be to use a pipe that extends upward. And this way, a lot of mechanics are able to loosen stubborn bolts. If you have a bolt on, let's say, the drain plug of your oil filter, of your oil pan, sometimes you can't loosen that bolt. And so what you do is you simply put a pipe over the wrench or over the socket, the ratchet, in order to loosen up that bolt. So now let's go over a problem here in solving for torque. The possible things we could know would be the torque, would be the force, or the radius. In this problem, we have a 5 Newton force is applied to a wrench at a position of 0.5 meters from the point of rotation. How much torque is applied? So pause the video at this point, take a couple minutes to solve the problem. When you're ready, unpause and see how well you did. Welcome back. So in this problem here, we have a 5 Newton force. That is our F. It is 0.5 meters from the point of rotation. That is referring to our radius, 0.5 meters. And we need to solve for the torque. To solve for the torque, we're going to multiply the force and the radius together. We have 5 for the force, 0.5 for the radius. And so we get an answer of 2.5 Newton meters. Try this next problem as well. Again, the possible things we could know would be torque, force, and radius. This problem says the most force that Hector can push with is 50 newtons. If a bolt requires a torque of 35 newton meters to turn, how far should Hector push from the point of rotation? So I'd like you to pause the video at this point, answer the question, and when you're done, unpause and see how well you did. Welcome back. In this point, in this problem here, we have that the force is 50 newtons. That's as much force as Hector can apply. The torque is 35 newton meters. And we need to solve for the radius. Since we're given the torque and the force, we're going to divide the two. So we have 35 divided by 50. This gives us a radius of 0.7 meters. Now, sometimes we have more than one torque applied to an object. When the torques are balanced, then we say that it is in equilibrium. So when balanced torques act on an object, there is no change in rotation. So for an example, let's look at this situation here. We have a girl and a boy on different sides of a seesaw. And they are of different weights. The girl weighs 200 newtons, where the boy weighs 400 newtons. And if we calculate the torque, which is the force times the radius, for the girl we have a force of 200 newtons and a radius of 3 meters. Therefore, she produces a torque of 600 newton meters. The boy, on the other hand, has a force of 400 newtons, and he has a radius of 1.5 meters. However, he still produces a torque, same as the girl, of 600 newton meters. And we see that, so even though the boy and the girl have different forces or weights, they can still play on the seesaw as long as the boy sits closer to the what we call fulcrum. That's the triangle part here. So because he has a large amount of force, he has to decrease his lever arm or radius in order to get the same amount of torque and ride the seesaw with the girl. Now in this situation here, we're asked what is the weight of the block hung at the 10 centimeter mark in order to balance the system. Now whenever we measure the radius, it is always from the point of rotation. In this case, the point of rotation is at 50. So the first thing we're going to do is solve for the torque of the weight on the right. So the force of that is 20. However, the radius we always measure from the center, or from the fulcrum, I should say. So we need that distance for our radius. And that distance is from 50 to 80. That means it is 10, 20, 30 centimeters. This gives us a torque of 600. Now on the other side, we also want an equal amount of torque to balance these situations, to balance the system. So we also want 600 in order to be balanced. We don't know that force, but the distance, again, we always measure the distance from the fulcrum, which is the 50 in this case. So the distance for the left-hand side is 10, 20, 30, 40 centimeters. To solve for that amount of force, we must divide each side by 40. And we get a force of 15 newtons. So even though the item on the left has less force, we can still balance it by having a greater leverage. So to finish things up here, what happens when balanced torques act on an object? Well, when balanced torques act on an object, the rotational motion stays the same. Just like the first law of motion, an object in motion stays in motion, and an object at rest stays at rest. What happens when unbalanced torques act on an object? Well, that's similar to the second law of motion. When unbalanced torques act on an object, the rotational motion change.